Okay, welcome back. So now I've written this up here. I want to go back to solve that question we had posed. Y of 0 equals y of pi equals 0. So first thing you want to do is cast it in this form again. And that means that y prime prime plus 2y equals negative lambda y. Bring that to the other side. It tells you 2y plus lambda y equals 0. Y prime prime plus 2 plus lambda y equals 0. I can solve this easily, just like before. I need it to be, my solutions will end up being sine square root of 2 plus lambda x. Right? And for this to equal to 0, I skip the step of cancelling out the cosine terms using the boundary conditions. Second boundary condition will show that this equal to 0. For that to be equal to 0, square root of 2 plus lambda equals n pi over L. Okay, our condition is pi, L equal pi, so this is just n. Or if you prefer, n squared minus 2 equals lambda n. Okay, so we have our eigenvalues, n squared minus 2. We have our eigenfunction, sine nx. This is n. Okay. So now we can go back up here, plug in n squared minus 2 here, plug in the norm of sine nx eigenfunction, which we already determined as in Fourier series case, we determined that as p, or in this case, which is just pi. Okay. Well, it'll be pi over, well, let me show that real quick. Okay, it's not exactly pi, because the norm we're looking for here is from 0 to pi of sine nx squared dx. In the Fourier case, we looked at from minus pi to pi, so this actually is pi over 2. Okay, so we go back and solve this. Should have left that one. Okay, so y of x is sum of n equals 0 to infinity. That inner product divided by n squared minus 2. Negative of that, just call it 2 minus n squared. That's negative lambda n times square norm, which is pi over 2, okay, times y of x. Okay, we've been so far scared of expanding this. Let's just do that real quick. It's not as scary as it looks. Y of x is sum of n equals 0 to infinity, 2 over pi 2 minus n squared. That integral, the inner product, is 0 to pi sine x sine nx dx. And we're multiplying that by yn of x. Oh, it's outside the board. Times yn of x. Okay. Once we do that, we realize again that this is the same integral we're solving for to show orthogonality. Remember, this equals 0 for n not equal to 1. Alright? 1 is the prefactor of x here, and that's n. For n not equal to 1. So we're really left with the square norm of sine x here. This is equal to 0 to pi of sine squared x dx. Right? You can confirm that, but this is it's directly from orthogonality. And we know that square norm is again pi but I'm looking at half of it, so it's pi over 2. We're looking at half the interval, and it's an even function. So it's pi over 2 for n equals 1. For other ones, it's 0. So we don't really have an infinite series anymore because everything else falls off to 0. 0 plus 0, 0, except the n equals 1 term, which is 2 over pi 2 minus 1 squared. That integral, which was pi over 2, yn of x, which is sine nx. Well, n is 1, so it's just sine x. Isn't this amazing? Pi over 2 cancels pi over 2, so I'm left with, and this is 1, just simply sine x. So that complex mess gives us sine x. Is this what we got with our previous method? Let's check it out. I can wipe this off. So with this new method, y of x is sine x. With the previous method, we said y of x was, if I remember, c1 cosine root 2x plus c2 sine root 2x plus sine x. Of course, when I apply y0 of 0, I get again that c1 equals 0, because c1 plus 0 equals 0. Which means y of x equals c2 sine 2x plus sine x. You see where this is going already? Apply y of pi equals 0. I get c2 sine root 2 pi plus sine pi, which is 0, equals 0. And clearly, the sine part can never go to 0, so c2 has to equal to 0. And if that's the case, that c2 is 0 and c1 is 0, all I'm left with is sine x. Okay, and this is kind of a tough, actually I believe you guys can handle this, but it illustrates again that this works. Our study of Sturm-Liouville problems is telling us now that we should be well equipped to solve most non-homogeneous differential equations. Okay. Let's go back to that form just to satisfy I think it was, it'll express it as the full integral here. AB f of, I'm just going to use a different variable here, f of t, yn of t dt over lambda n, that's square now, times yn of x. I'm using t here because I want to group yn of x in with this, and I know that there's a separate integral, just so you realize there's no problem. Okay, I'm going to swap the series sum with the integral. I get AB sum of n equals 0 to infinity f of t, yn of t, yn of x dt divided by the square number of yn squared, the square number of yn, negative lambda n. Okay, if I were to write this as y of x equals AB, write this as y of x equals AB, sum of n equals 0 to infinity. I'm just going to pull the, what do you call it, the f of t to the other side. Okay, so what I want to do, yes, that's what I want to do. Okay, pull the f of t to the other side. So it's yn of x, yn of t, f of t dt divided by negative lambda n yn squared. You recognize This is very similar to what you did last class, in your differential equations class, or NMath A. You recognize that you have something that looks like this, where this is your Green's function, right? Where your Green's function is defined as the sum of n equals 0 to infinity yn of x yn of t over negative lambda m square arm of yn. Okay, so this is another form for the Green's function. You had one in your first class using the Wronskian. You had another one. You've had different forms so far. This is another form that we clearly see works here. The beauty of this form is I can use it for different differential equations as long as I know my orthogonal set of functions, as long as I can determine my eigenvalues for the Sturm-Liouville problem and my square norm based on the orthogonality rules from Sturm-Liouville problem. Okay, so I'll just leave this here for now. What do you need to know from what we've covered? This is fancy but not necessary. The original form is good enough for you to remember. I don't require you to figure out what the Green's function is, but learn how to use that integral to solve the full solution to a non-homogeneous problem. If you end up in a situation where it wasn't as clean as what I gave you, and you end up with some series still, don't freak out. All this is that you're having a solution in the form of a series form, and the truth is, if you found the solution in some other way and you end up with a closed form, you'll find out that this series form is simply the Fourier series expansion of whatever closed form you got. So assuming I didn't end up with sine x, assuming I ended up with some series, then sine x, that series will be the expansion of sine x. But of course we know that the series expansion of sine x using it's pointless doing that for sine x using a Fourier sine series, because your coefficients are all 0 except for when sine is sine. Sine x is sine x, except for when n is 1. So anyway, that was just one interesting thing to note. So again, what we're doing so far is understanding how we can get different sets of orthogonal sets of functions, different types of orthogonal sets of functions based on your Sturm-Liouville problem. And those sets of functions will have different orthogonality rules depending on the weight function p of x for the Sturm-Liouville problem. I'm pointing at nothing right here, but again, you can play this back and confirm what I'm talking about. So we'll continue from this in class. Have a good night.